We can hear you, ma.
Can you hear me now? Okay, thank you very
Yes, ma'am.
much.
Yes, ma'am.
Please, I want to confirm something. Is today the fourth lecture with you or the fifth? Is today my fourth lecture with you or the fifth lecture? Can you answer me? Thank you very much.
I think fourth.
I think it should be 4. Okay, thank you. It's the fourth one. So I have the correct slide. So today we are going to start the lecture first. Then at the end of the lecture, we'll take our questions. We'll start with the lecture. We started the Harris Law and the Roult's Law the last on Friday. So we are going to conclude that today. So by Wednesday, we start with thermodynamics. So like we say that dilute solutions obey Henry's law. We started looking at ideal mixtures or ideal solutions. And we actually looked at some of the characteristics that make a solution to be ideal. And we say that they have to be similar in size. And again, the pure component has to have the same characteristic or the same internal force as at when it is mixed with another liquid. So that was what we concluded the last class. So today we are still looking at ideal mixtures and now enthalpy change of mixing. Now, like I said the last class, that when you make any mixture, when you mix two liquids, what happens is this: for them to be miscible, for you to mix them, you have to break the bond between the pure liquid, between each of the pure liquid, and you now make a new one. When you're breaking this existing force, which is an intermolecular attractive force, you need energy to do this. And when you're now making a new intermolecular force, you release energy. This is an example of what we are saying. This is HCl, which is a liquid. Now, this HCl has intermolecular attraction between, this is like a pure component or a pure liquid. This is your water. It's a pure liquid on its own. On its own, they have these intermolecular forces that is holding them together. This is between hydrogen and oxygen, and this is between your chlorine and your hydrogen. Therefore, when you mix your water and your HCl, what happens is this: you have to break these intermolecular forces. You have to break them so that you will now have your water and your HCl in attraction with each other. So for you to break those intermolecular forces that exist between this pure liquid, you need energy. Now, when you're not making a solution of HCl and water, energy is released. This is another example of a liquid. This is chlorine. You can see that this chlorine and chlorine, it has an intermolecular attraction between the two of them. We don't want to go into the type because it's not what we want to do. Now, if all these attractions are the same, what do we mean? If the intermolecular, is the energy needed to break the bond is equal to the energy released when you break the intermolecular forces. That means that there is no heat involved or absorbed, because if you need a plus 10 energy, and when you, if you need minus 10 energy, and when you're done, you're releasing plus 10 energy. Minus 10 plus 10 is equal to 0. So it's eventually, it means that heat is neither given out or taken. Now, what this is telling us is that for an ideal mixture of two liquids, that you have zero enthalpy change of mixing. For an ideal mixture of two liquids, there is zero enthalpy change of mixing. Now, if there is an increase in temperature or decrease, when you mix the two liquids, the mixture cannot be ideal, because definitely there is going to be a change in some of the attractions. So that mixture is not going to be ideal, which means that if there is effect of temperature changes a solution from being an ideal solution, ideal mixture, to non-ideal mixture. Now, there are several ways of stating Roult's law depending on the situation that you're talking about. You can state Roult's law as applied to two volatile liquids or as applied to non-volatile solutes. We are going to take them one by one. Let's look at Roult's law as applied to two volatile components or liquids. It states that the partial vapor pressure of a component in a mixture is equal to the vapor pressure of the pure component at that temperature. Remember, at that temperature. So the temperature is constant, multiplied by its mole fraction or mole ratio in the, mole fraction, not ratio, in the mixture. Let me explain. What we are saying is this, that the partial pressure of a component in a mixture. Remember that for you to have a mixture, you need at least two components. Let's take, for example, now that I have component A and I have component B, and I want to mix them together. Mixing them together, I'm going to form AB mixture. So we are saying that if I want to look at the partial pressure of component A in that mixture, not as a pure liquid, in that mixture, is going to be the partial pressure of component A in that mixture is going to be the partial pressure of my A when I've not mixed it with B, multiplied by the mole fraction of A, that is liquid A. So what we are saying is this, that if I want to calculate the partial pressure of component B, it's going to be the partial pressure of component B in that mixture. The partial vapor pressure of component B in that mixture is going to be the vapor pressure of my pure component B multiplied by mole fraction of component B. It's in that way that I can get the vapor pressure of that component in the mixture. So can you hear me now? Sorry about that. Can you hear me now? So let's look at the examples given. This is exactly what I am saying. That for a mixture of liquids A and B, this is the partial pressure of component A in the mixture, and is given by the mole fraction of component A as a pure liquid multiplied by the vapor pressure of component A as a pure liquid. That is before mixing. And for B, it is the mole fraction of B multiplied by the vapor pressure of pure component B. So if I need to calculate the total pressure, the total partial pressure of the mixture, is going to be this of PA plus PB. That is the vapor pressure of component A in the mixture plus the partial vapor pressure of component B in the mixture. Oh, it's here. So the total vapor pressure of the mixture is equal to the sum of the individual partial pressures. Remember that P dot values are the vapor pressures of A and B when they are in their pure state. That is, if they were on their own as pure liquids. Now, before I go further, I want us to go to, I asked you to do something. Can you please go to the chart now? We need to calculate the quantity of CO2. I don't forget assignments anyway. I asked you to calculate the quantity. What I did, Yusuf, what I want you to do is, I want you to give me step by step, that is, the first thing that you did was to calculate the what? The concentration. Then you now get the molar concentration. The mole and the what? And the quantity. Good. Now, what was your the value for the concentration? In fact, let's start with the formula. The formula says the concentration is what? The constant, isn't it? The constant multiplied by okay. So what are we giving? What are we giving as our care? Let's start. Yes, that is what we are using. I know. We are using C is equals to KP. Yes, I know. 29.76. Okay. So 29.76 multiplied by the pressure is what? Our P is what? You have the question with you. I don't have it. 2.4. So 29.76 multiplied by 2.4 is what? 71.424 M. Good. 71.424 M. Now we have our C. Then there's a relationship between your concentration, your molar mass, the number of moles and the volume. Remember that you're giving the V there as 1 liter. So it's going to, that means that your concentration is still the same thing as your number of moles. Am I correct? Yes. Mole is molar concentration times volume, which is going to be 71.424 times 1. 71.424 times 1, isn't it? So we still have the same thing as our mole. That is the same figure. It's just that the unit is going to change. Exactly. It's going to be 71. Good. Now we have the mole. Can we now calculate the mass? That is the quantity, because that is the question. The question says mass. So what's the relationship between your number of moles, mass, and molarity? It's 44. 71.424, because we are talking about CO2, so it's 44. So the number of moles, C is equals to N over MM. The number of moles is what? Mass over molar mass. Good. Then mass is what? Mass is going to be mole times molar mass, isn't it? If you can hear me, please answer me on the chat. Good. Mole times mole. Good. Can you now give me the answer? So we are multiplying 71.424 by 44. 71.424 by 44. Good. I think it's something close to what you're giving me. 3142 points. Who is saying height? Who is saying H? Your unit is going to be in gram. The unit is going to be in gram. The unit is going to be in gram. Okay. Thank you very much. Let's go to our slides now. So we want to look at how to calculate the mole fraction for the respective pure liquids. How to calculate the mole fractions for the respective pure liquids. Now, for you to calculate the mole fraction for component A, it's going to be moles of A. I hope you have your biro and your writing materials, whichever way you want to look at it. Moles of A over the total number of moles. When we talk about moles of A now, we're actually talking about just one component or one pure liquid, but the total number of moles is going to be the total number of the liquids that make up the mixture, assuming that we are looking at this A and B. So the mole fraction of A is going to be moles of A divided by moles of A plus moles of B. That is what is going to give us the total number of moles here. So let's look at a real example. The question says, suppose you had a mixture of 2 moles of methanol and 1 mole of ethanol at a particular temperature. The vapor pressure of pure methanol at this temperature is 81 kPa, and the vapor pressure of pure ethanol is 45 kPa. Maybe we are asked to calculate the total vapor pressure. To calculate the total vapor pressure. Now, we've been given that each of the components has, one component has 2 moles, the other component has 1 mole. So the total number of moles is going to be 3. But we need to calculate the mole fraction for each of them. Let's start with ethanol. Ethanol is 1 mole of ethanol. That means that the mole fraction for ethanol is going to be what? It's going to be 1 over 3. The mole fraction is going to be 1 over 3. But remember that we've already said that the vapor pressure of components of ethanol in the mixture is mole fraction multiplied by the vapor pressure of that component. And for ethanol, the pressure here is 45 kPa. The vapor pressure of pure ethanol is 45. So it's going to be mole fraction of ethanol, which is 1 over 3, multiplied by 45. So it's going to give us 15 kPa. Now for methanol, because we have 2 moles of methanol, it's going to be 2 over 3 times 81. The vapor pressure of methanol at that temperature is 81. So it's going to be over 81. So you have the vapor pressure for methanol in the mixture is 54 kPa. Therefore, the total vapor pressure for this mixture now is 54 plus 15, which is giving us 69 kPa. This is as simple as ABC. It's very, very simple. It's very, very simple. Now, let's look at for non-volatile solutes. For non-volatile solutes. Remember that for non-volatile solutes, we're actually looking at something that will not escape. Something that will not escape. So if we say that okay, somebody is asking the difference between Roult's law and Dalton's law of partial pressure. I'll give you the answer. But Roult's law has to do when you're dealing with ideal mixture. When you're dealing with ideal mixture. In Dalton's law of partial pressure, you're actually not looking at whether the temperature is changed or not. Because for ideal mixtures, once you change the temperature, they are not going to obey Roult's law again. But even for Dalton's law, there is no significant effect of temperature change on Dalton's law. So that is basically the difference between the two. So you're not going to have a significant change when you change the temperature for Dalton's law of partial pressure. Now, let's go back to what we have. So, and if you look at the Dalton's law of partial pressure, it's actually looking at when you talk about gases, purely gases. So your mixture has to be made up from gases. But look at what we are looking at here. We are looking at mixture. We are looking at liquids. We are not only concentrating on gases, but your Dalton's law has to concentrate on gas because it obeys the ideal gas law, which is PV is equals to nRT. PV is equals to nRT. I don't know who asked that question, if you're okay with my answer. When you're talking about Dalton's partial pressure, you're actually looking at pressure from gases. So each of the components is made up of gas. Each of the components is a gas. And it has to obey ideal gas law, which is PV is equals to nRT. So you're talking about something that has to do with pure gases. But when you talk about, when you look at Roult's law is dealing with liquids. It's dealing with mixtures. I don't know if you're getting me. If you're okay with the answer, can you go back to the chart and let me know? Are you okay? Let me see the person that asked the question. That was a good one. It's a good question. And I think maybe I did some kind of justice to it. I am not sure. Okay, Joseph, are you okay? Okay, that's basically the difference between the two. Your Roult's law deals with ideal mixture. So you're talking about two liquids, two mixtures coming together. One must be a liquid, because in Roult's law, you look at volatile liquids and you look at non-volatile solids, the one that can volatilize and the one. So, but in Dalton's law of partial and Roult's law, it has to obey, ideal mixtures obey, or ideal solutions obey Roult's law, while ideal gases obey Dalton's law of partial pressure. So Dalton's law of partial pressure has to do with gases, and it has to obey your PV is equals to nRT. But when you talk about your Roult's law, it's definitely dealing with it's dealing with liquids and all that. Thank you very much, Joseph. Now let's go to what we have. Now we want to look at Roult's law as applied to non-volatile solids, and I want to explain it as I will explain to a layman. Remember that when you talk about pressure, when you talk about vapor pressure, that means that something has to evaporate, something has to evaporate. And maybe when you have a cover on your container or a lid on your container, when your gas phase evaporates, they will begin to hit the cover of the liquid, or they will begin to hit the walls of the liquid, and as such they will develop pressure. It is that pressure that is known as vapor pressure. Now, when you have a solute that does not volatilize, that cannot evaporate, do you think that it will produce a vapor pressure? No, it's not going to produce a vapor pressure, because it is not evaporating, and it's not producing a vapor, and it's not hitting the walls of your container or the lid of your container for you to exert a pressure on the walls of. So that means that there is nothing like vapor pressure for your non-volatile solute. So when you talk about non-volatile, so the vapor pressure of non-volatile solute, you're actually looking at just the vapor pressure of the solvents that make up that mixture, because you have two things to make up a mixture or a solution: your solutes and your solvents. Now in this case, one of the components is non-volatile, while the other, which is your pure solvent, is volatile, and that is the one that will have a pressure. So in dealing with non-volatile solutes, the equation is not of the same definition with that of two volatile liquids. This one is the vapor pressure, and is equal to the vapor pressure. The vapor pressure of the solution of a non-volatile solute is equal to the vapor pressure of the pure solvent at that temperature, multiplied by its mole fraction. So you see now that we are just looking at just the mole fraction, or whatever that constitutes the solvent. Unlike the previous example that we looked at the two liquids, because both of them are volatile and both of them will have vapor pressures. Good. So again, the P dot is the vapor pressure of the pure solvent at a particular temperature. The X is the mole fraction of the solvent. The mole fraction of the solvent. So when we look at the mole fraction of the solvent, it is equal to the moles of the solvent over the mole fraction of both the solvent plus that of the non-volatile solute. So let's look at some examples. The first question here says 80 grams of, and there is something I want us to look at here. There's something I want us to look at here. Now, sorry, let's go back. Now, when we started with the looking at what happens in when you start getting an ideal mixture and how we got the ideal mixture, remember those blue and the red balls that we looked at, and we say that there is not going to be a change in anything, so that whatever you have the pure component to be made up of is what you're going to have it made up of when you have mixed it with another component. So that is when you form a mixture of it. Now, look at this. There are most times when you look at salts, their number of moles changes when you dissolve them in water. We have to be careful to know the kind of components that we choose. If you look at most of the examples that we'll be giving you here will be sugar, glucose, fructose, and all that. When you look at salts, take for example your sodium chloride. If you have one sodium chloride and you dissolve it, you put it in water, it's going to dissociate into sodium ion and chloride ion. Each of them will have one mole. So you're forming 1 mole of Na plus and 1 mole of Cl minus. So you have 1 mole of sodium chloride and you're coming up with 2 moles in solution. You see that solution cannot obey Rath's law. That particular component, that particular salt cannot obey Rath's law, because you started with 1 mole of sodium chloride, and when you put it in water, you have 2 moles of each of the species, Na plus and Cl minus, 1 mole each. So that does not hold. So that is what I want to bring out here before I continue. Now you have 80 grams of your.
And since when did they start sprinkling the donuts with sugar?
I don't know why this thing kept on pumping up. You have 80 grams of your glucose, and sorry to go. So we have to calculate the expected vapor pressure. We have to calculate the expected vapor pressure. Now, how do we get about this calculation? Now we need to bring out we need to write now. We need to write. First of all, let's go to the chat box. We'll do it together. Let's go to the chat box. First of all, we know that now we have glucose. Is it volatile? Is glucose volatile? No. So we are going to use this formula. This is the formula we are going to use. The partial pressure, the vapor pressure of a solution of non-volatile solute is equal to the mole fraction of the solvent multiplied by the vapor pressure of the solvent. Let me see what you people have on the chart. Okay, good. Thank you. It's not volatile, so we are considering it as what? As a non-volatile solute. So this is the equation that we are going to use now. That is the equation we use for our calculation. Now, what is the first thing that we'll do? What is the first thing that we'll do? We are going to calculate the mole fraction of our solvent. And our solvent here is water. Our solvent here is water because we are told that it's dissolved in 100 mils of water. So we need to calculate the mole fraction of water. How do we calculate the mole fraction of water? Quickly give me that. Good. To calculate the mole fraction of water, it's going to be number of moles of water, isn't it? Over the number of moles of your water plus your glucose. Then how do we get the number of moles of our water? Can we do that? Remember, there is a relationship between density, mass, and volume. So we can get the number of moles of our water if we can get the mass, because we have volume here, which is 100 mils, and the density of water is approximately 1 gram. Good. Exactly. So can we get the mass? The mass is going to be what? Density times volume, isn't it? Which is 100 times 1 gram. And that's going to give us what? 100 grams. Exactly. Joseph, thank you. So we have the mass of water as 100 grams of water. Now, can we then get the number of moles of water? Can we get the number of moles of water? Thank you, Akbala Nozie. Thank you, everybody. Akinyemi. Can we get the number of moles of water? Is mass over what? Molar mass. And it's going to be 100 over what? 18 grams. Is it 100 over 18 or 18 over 100? Who is saying 18 over 100? It's 100 over 18, exactly. So 100 over 18 is going to give us what? Are we sure? Our mass, no. The number of moles. The number of moles should be gram over. Good. The number of moles. I am taking it the other way. The number of moles is going to be our mass times molar mass, please. The number of moles is going to be our mass number of moles is mass over molar mass. Okay, so what's the molar mass? What's the number of moles? Okay, you're correct. Oh, you're correct. Oh. No, we are not changing our 100 mils to liter. Leave it in 100. Density times volume in DMQ. We can change at the end of the day. So we have the number of moles as what? 5.56 moles. Okay, that is for our water. Can we now calculate the number of moles of the glucose or whatever we are giving? Is 20 grams over 80 over 324. Are you sure it's 324? 12 times 12 plus 22 times 1 plus 16 times 11. Are you sure it's 342? Are you sure it's 342? Okay, if it's 342, because I can't work it out here. If it's 342, then it's going to be 20 over 342. 20 over 342. So what's the number of moles for our glucose? 0.234. Good. 0.234. So now, the mole fraction for water is going to be, what did we get? 5.56 over 5.56 plus 0.234. Can we get the mole fraction now? 5.56 divided by 5.56 plus 0.234. I need you to calculate the mole fraction of water now. Substitute the mole fraction for the respective component. 0.96. Praise, are you sure? Any other answer? 0.95. Rex. 0.96. 0.98. Israel. Which one do I now take? Farouk Idris. I don't know which one to take, so you better calculate it well. So let's go with 0.956. Let's go with 0.956. 0.9, okay, 0.96. 0.96. Now take 0.96 to the equation now. Our P solution is going to be what? 0.96 times 23 points. Let's see what we have here. Okay, no. The P dot is 0.0317. 0.0317. So 0.96 times 0.0317 is what? 0.96 times 0.0317. What's the answer? Quickly give me the answer. 0.0304. Exactly. But you have to write the unit. Is in torr. Is in torr. 0.304. Some people say 0.30. Some people say 0.03. Which one do I take? But please give the correct answer, because your exam is OBJ. It's multiple choice question, MCQ, and options like this will come 0.3, 0.03. So you need to be careful. You need to be sure. And the correct units will be there. The wrong units will be there, even with the correct value. So you have to be very, very careful in choosing your answer. Then the next question says, how many grams of glucose? Let's look at the second question. How many grams of glucose must be added to 250 grams of water at 40 degrees Celsius to create a solution with a vapor pressure of 54 torr? Now, remember now, we are going to get the number of moles. Now we have our P solution, which is 54. That is the vapor pressure of solution. It's going to give us the mole fraction of water plus the vapor pressure of water, which is 55. So we have 54 is equals to X water times 55. Okay, that times 55 torr. So it's going to be X 54 is equals to X water, which is the mole fraction, times 55. So what is the answer? 54 times 55 is what? 54 times 55 is what? Okay, 54 over 55. Is over. If it's over, it's over, it's over. Abayo Ayobami is over, it's over. Because we are looking for X water. So it should be over. Good. You have 0.982 is equal to X water, isn't it? 0.982 is equal to X water. Now, from there, you can actually calculate the number of moles of your glucose. The number of moles of your glucose, and from there, you can get the mass. You can calculate the number of moles of your glucose and you can get the mass. But before you get the mass, you need to get the number of moles of water. It's going to be 250 over 18. Remember now you've been given that the mass of water is 250. So you get the number of moles of water, which is 250 over 18. So it's going to be 0.83 is equals to 250. I mean, whatever you have as 250 over 18, good. That is 13.89 over 13.89 plus N glucose. So it's N glucose that you're looking for. So I guess you can solve that question and give me the answer the next class. So I want us to go. So we finish what we have for today. This is another one that you can try at home, but you don't understand how we got 0.98. You say you don't understand how we got 0.98. Okay, we got 0.98 from the equation. Remhen, are you listening? The equation says, let's go back to the equation. The equation says P solution, which is given as 54, is equals to X solvent, which is your water, multiplied by P dot of solvent, which is P dot of water. Now you are giving this as 54, and you're giving this as 55. Am I correct? Yes. You're giving this as 54, and you're giving this as 50. If I have 54 is equals to unknown X solvent times 55. If I want to make this the subject of my formula, what do? I will say 54 over 55, isn't it? So that's how we got 0.98. If you're okay, Raham, can you please put it on the chart that you're okay? Good. Thank you very much. So that's how we got 0.98. So let's move forward. I'll give you the question at the end of the class, and then let's go. I don't think it's 93.96 grams of glucose, but we'll look at it. Yusuf, go back. We'll look at it the next class. Then let's look at effects of, am I sure? Okay. Effects of a non-volatile solute on the melting and freezing points of the solution. Now, the boiling point of the solvent in a solution, it's higher than that of the pure solvent. That means we're just trying to look at, I don't want to go into colligative properties because this is not, you're not. Hey, Emanuela, I'm teaching, you're busy asking me if the slide will be available after the class. What do you have to do with the slide? I've told you people in this class, so I don't want that. I don't want this kind of questions. Listen, so if I don't give you slide now, you won't be able to answer any question that will come out from what we have done today. Your mind is on slide. Instead of your mind, on slides. Instead of you listening to the lecture, your mind is on the slide that will be given at the end of the lecture, instead of listening to the lecture and asking questions if you have questions. You see that I've been going through the lecture to the chat box, and I've been answering people's questions. You're busy waiting for the slides. Wait for the slides. I don't know, it's your luck if the slide will be available. I don't know if it will not be available. Good. Now the boiling point will be affected, and the freezing point, which is referred to as the melting point, will also be affected. Now let's look at how non-volatile solutes will affect the melting or the freezing, the boiling or the freezing point of a solution. Now, we say that the boiling point will increase and the freezing point will decrease. And this is actually referred to as boiling point elevation. The boiling point elevation is directly proportional to the molality of the solute. You know, when we talk about molality, we know the units of molality. It is no longer the, the mole per dm cube. Now we are actually talking about quantity. We are looking at the kilogram. So we are looking at the kilogram. Now the equation for this is change in the boiling point elevation is going to give us the molar boiling point elevation constant, which is our KPB, multiplied by the molality. So this is our molality, the molality of the solute. And this is the constant, the molar boiling point elevation constant, or the boiling point elevation constant. And this is the change in the temperature of the boiling point. Because we said there is going to be increase in boiling point. So definitely there is going to be a change. You're going from one to the other. Even for freezing point depression, there is always a change because you're going from the normal boiling point to an increased boiling point. So this is one of the questions here. You're going to see that in your slide, if the slide we've made available. If not, we'll look at it the next class. I want to finish this. So for the freezing point, I don't know. For the freezing point depression, the freezing point depression is very similar to boiling point. Again, the change in the freezing point depression is equals to the freezing point constant multiplied by molality of the solute. We are multiplying by the molality of the solute because you have it's a non-volatile now. So when you want to calculate for this, you're actually looking at the molality for the solute, and that's why we are using molality and not molarity, because molarity has to do with volume, something in liquid. Molality has to do with solid, so we're actually looking at the kilogram, mole per kilogram of our solute. Now, so if you look at the freezing point depression, for the freezing point depression, there are more atoms of the pure solvent going from a solid to liquid than from the liquid to solid. Remember that we say that solutions that do not obey Rath's law are solutions that are non-ideal. And solutions that are not ideal are solutions that are being affected. They are being affected by a change in temperature. So again, if you have a difference between your solute-solvent interaction, if the solute-solvent interaction is different from solute-solute interaction or solvent-solvent interaction, the solution is likely to be a non-ideal solution. Remember when we looked at those blue and the red balls, we actually said that the solute-solvent interaction is the same as solute-solute interaction or solvent-solvent interaction, and so our mixture tends to be ideal mixture or ideal solution. Now, if you have intermolecular forces between components in a dissolved solution, it can cause deviation from the calculated vapor pressure. Yes, it can cause deviation because you have dissolved solute, that is, you have something dissolved in the solution. So it can actually increase or decrease your vapor pressure. So decreasing or increasing your vapor pressure makes it, makes that solution to deviate from Rath's law, and automatically it will deviate from the calculated vapor pressure. Let's look at two types of deviations from Rath's law. We have the negative deviation and we have the positive deviation. The negative deviation is when the vapor pressure of your mixture is lower than expected from Rath's law. It's going to be a negative deviation. What this means is that by default, you know that from Rath's law, the vapor pressure of this particular mixture, for example, is 30. If after calculating the vapor pressure, and maybe there, because of the dissolved components you have, the vapor pressure changes to maybe 20 or 28, you see that the calculated is lower than the expected. And so this type of deviation is classified as negative deviation. Now, if the vapor pressure of your mixture is higher than expected from Rath's law, this particular deviation is called a positive deviation. So you have two types of deviation: negative deviation and positive deviation. Now we're going to look at the boiling point diagram of binary miscible liquid mixture. Liquid with high vapor pressure will have a lower boiling point. I'm going to explain this. Listen to me. Listen to me. When you have liquid with high vapor pressure, you have more escaping from the solution. And that means that you're going to have high concentration of the solution, and as such, the boiling point will reduce. It's a lot of things will be evaporating. Now, when you have liquid with low vapor pressure. The liquid with low vapor pressure, this one with high vapor pressure does not need much temperature to make it to evaporate. Do you understand? Liquid with high vapor pressure, the vapor pressure is already high. So you just need a little temperature to make the vapor to go, to turn the gas phase into vapor. So it does not require a higher temperature. That is why the boiling point will be low. So as very low, it starts to boil because the vapor pressure is already high. So once you use a low temperature, at a low temperature, it's already vapor. But when the liquid has a low vapor pressure, you need to add in or put in more temperature, a higher temperature, for you to make it to do what? To boil. I don't know if I'm communicating. I need to understand it very well. Liquid with high vapor pressure, the pressure is high. So with little temperature, it will begin to do what? The vapor will begin to, it's already vaporizing. So it easily escapes. So you don't need much temperature or higher temperature to make it to boil. So that's why we say liquid with high vapor pressure will have a low boiling point. But liquid with low vapor pressure, the pressure is low. So you need to put in a higher temperature for you to get it to the boiling point, or for you to make it to escape. So you have higher boiling point for that particular class of liquids. Now, let's look at this diagram. This diagram is just telling us that for liquid, this boiling point of pure B is telling us that this liquid is a liquid with high vapor pressure. And liquid with high vapor pressure will have what? A low boiling point. This is your boiling point here. This is your boiling point here. So this is, you know that here, this is low. Here is your mole fraction. You know that your mole fraction, addition of mole fractions will give you 1. So if you start this one with 1, this is 0. So A, 1, here it is 0. So when you have a pure liquid with a high vapor pressure, the boiling point will be low. And that is why the boiling point of B is here and the boiling point of A is here. Now, what this is telling us is this: you can actually get the boiling point of any component of your choice. When you have the mole fraction of this component Ca, maybe the mole fraction here, let's say that here is about, let's say 0.98. I don't know, I'm just in as an assumption. I can actually calculate from this diagram or from this graph. I can always extrapolate and get the boiling point for that particular component using this boiling point diagram. If I extrapolate from here and it touches here, I will read off the temperature here. C1 for this particular component, C1 is giving me what? It's giving me the boiling point for this component C1. Then, if I want the vapor composition of T1, I will just extrapolate to this particular curve again, because this second curve is giving us the vapor composition, while this blue one is giving up the liquid composition. So the liquid composition has to do with boiling point, while the vapor composition has to do with vapor pressure. So you will use this diagram to calculate both the boiling point and the vapor pressure of an unknown component. All you need to do is to get the mole fraction of that component, and you will now extrapolate and get the boiling point in physics vapor pressure. So again, you can always use this. This is what you can use it in fractional distillation of a liquid. Assuming that this is my component C1, what I will do is, if I get the boiling point and I get the vapor pressure here, this is another component B. I will be doing it, and this will be reducing till I will get to pure component. But it's just that by the time I will get to this particular, getting the pure components of my B, the components will be in a small quantity, using this to carry out my fractional distillation. So that is all we have. I think that is all we have for today. And then we'll just use 5 minutes to go back to what we have here. Now, the first question says, the following mathematical equation expresses Henry's law. Go to your chart. I'm just going to use like 5 minutes. I know that our time is up. Just give me 5 minutes, I will be done. Just give me 5 minutes, I will be done. Okay, I did not.
Please.
You see, because I did not, don't mind them. Because I did not, I forgot to mute all of them. That's why they are making noise in my class.
Do have daughter.
Don't worry, you're making noise.
Simi.
Now let's go to the question. Your hands on the chart. Are we there? The following mathematical equation expresses Harry's law. The following expresses Harry's law. Except, okay, the following expresses Harry's law except C is proportional to P, K is equals to CP, C is equals to KP, K is equals to C/P, C over P. Listen, the following mathematical equation expresses Harry's law except A, C is proportional to P. You're not making attendance. You're not marking any attendance. Answer my question, Joe. B, K is equals to CP. I can see an answer already. And I'm putting down the names. C is proportional to P. K is equals to CP. C, yes, the answer is B. K is equals to CP. Because A is correct, please. C is proportional to P. Is when we now introduce the constant that will now remove the proportionality sign and put our K. Now, when a non-volatile solute is dissolved in a pure solvent, the vapor pressure of the pure solvent dash. When a non-volatile solute is dissolved in a pure solvent, the vapor pressure of the pure solvent increases, decreases, remains the same, equals 0. Give me my answer. When a non-volatile solute is dissolved in a pure solvent, the vapor pressure decreases, correct. Ayobami, can you go back and listen to the question again? We are adding a non-volatile solute to a pure solvent. The vapor pressure, we just did an example now where we calculated the vapor pressure of our P dot. The vapor pressure of the pure solvent will decrease. It will decrease. Now, Harry's law gives the relationship between dash. Harry's law gives the relationship between the pressure and solubility of a gas in a particular solvent. The pressure and solubility of a gas in a particular solvent, that is A. B, the temperature and solubility of a gas in a particular solvent. C, the composition of the mixture and solubility of a gas in a particular mixture. D, the volume and solubility of a gas in a particular solvent. Which one? Pressure and solubility is A, correct. Pressure and solubility. Pressure and solubility. Does the reaction of HCl and water obey Henry's law? Does the reaction of HCl in water obey Henry's law? Does the reaction of HCl in water obey Henry's law? The answer, please. We did that the last class, before today's class. Does the reaction of HCl in water obey Henry's law? No, it does not obey Henry's law because you have it reduces into H plus and Cl minus. Thank you very much. We did it the last class. So let's take more questions. This question says, the following are examples of ideal mixture except, the following are examples of ideal mixture except hexane and heptane. Hexane and heptane A. B, benzene and the methyl benzene. C, ethanol and water. D, propan 1-ol and propan 2-ol. Which one is not an example of ideal mixture? Which one is not an example of ideal mixture? Hexane and heptane. Yes, ethanol and water. Ethanol and water is not an ideal mixture. Ethanol, I won't ask you to give me the reason anyway. I've asked you this one. The addition of non-volatile solutes lowers the vapor pressure. A real solution is that which obeys Rath's law, does not obey Ratt's law, obey Henry's law? Which one? A real solution. I didn't say ideal. A real solution. Does a real solution obey Ratt's law? Does he obey Ratt's? Just write obeys Ratt's law or does not obey or obeys. Okay. Does not obey Ratt's law. Good. It does not obey either Ratt's law or it does not obey Henry's law. Henry's law obeys what type of solution? Henry's law obeys what types of solution? I'm not giving you option, please. Henry's law obeys what type of solution? Henry's law obeys what type of solution? No. Henry's law obeys what type of solution? Dilute solution. Good. Dilute solution. Ratt's law obeys what type of solution? No. Henry's solution obeys dilute solution. Henry's law obeys dilute solution. Henry's law obeys dilute solution. Ratt's law obeys what type of solution? You have to be fast, though. I said fast fingers. Ratt's law obeys what type of solution? Ratt's law obeys ideal solution. Good. Ratt's law. If you're giving me the answer, specify whether you're talking about Henry's law or you're talking about Ratt's law. Don't just say ideal. Okay, ideal is Ratt's. Good. Felicia, you're correct. Ideal is Ratt's law, while dilute is Henry's law. Now, let's look at this question. I like this question. It says, given that the freezing point of water is 0 degrees Celsius, given that the freezing point of pure water is 0 degrees Celsius, what would you anticipate the freezing point of a solution of calcium chloride dissolved in water to be? What would you anticipate the freezing point of a solution of calcium chloride dissolved in water to be? Is it the same 0 degrees Celsius? Is it 10 degrees Celsius? Is it minus degrees Celsius? Is it 100 degrees Celsius? It will decrease. Good. So it will decrease. Now, it's lower than 0. So the options here are 0, 10, minus 10, 100.
Solutions are different.
0, 10, minus 10, 100. So which one? Give me a value. I need the number. Yes, it's lower than 0. Now give me the number. No, 10 is not lower than 0. 10 is not lower than 0. Bakari, 10 is not lower than 0. The options are 0, 10, minus 10, 100. Minus 10. Because you are correct by saying that it's lower than 0. So the only value that is lower than 0 in this option is minus 10. So you're correct. Thank you very much. You're very correct. Now, let's look at some other questions. I have one question that I wrote out somewhere. I'm sorry, I'm coming. Okay. Oh. Okay, ideal mixture has dash enthalpy of mixing, enthalpy change of mixing. Ideal mixture has dash enthalpy change of mixing. Is it 1? Is it 0? Is it the same?
0.
Ideal mixture has
0.
dash enthalpy change of mixing. 0, 1, the same. Can I have my answers? 0 enthalpy change of mixing. Thank you very much. 0 enthalpy change of mixing. 0 enthalpy change of mixing. Now, I think we are going to end the class here. It's time. Our time is past. Tomorrow we will look at. Tomorrow we are going to go into thermodynamics, so it's going to be much faster, please. Thermodynamics is, I think you will understand it fast. I don't know, but I pray you catch up fast so that I wouldn't waste time. We have double the slide that we are using today. So thank you very much, and do enjoy your day. See you on Wednesday. Did I give you any assignments? Yes or no? Yes or no on the chat? Yes or no? Is there any assignments for you? You're not answering me. Is there any assignment, Mohammed? Is there any assignments? Is there any assignments that we will look at the next class?
No, ma. No, ma.
Answer me now. Okay. This is your assignment. You have an assignment here. Copy the assignment, please. Snap the assignment. Whatever you want to do with it. This is your assignment. Again, we need to look at the steps. Don't just tell me that the answer is this. You tell me, first of all, how you calculated this, how you did this, because now we are looking for P solution. So P solution is equal to X water plus P dot water. So we have been giving P dot water as 149.42, and you can actually calculate the number of moles of our water. We've been given 225, which is 225 grams. We use it to get the number of moles of water. Remember that the question is to get the mass. Okay, to get the vapor pressure of water over the solution. Okay, we are calculating P solution. We are calculating P solution. You cannot see the screen. What is happening now? You can't see. Can you see now? Okay. If you can't see, I'm going to check your LMS. Check your LMS. It will be on your LMS. It will be uploaded on your LMS. It will be uploaded on your LMS. Thank you very much and have a good day.